Alright, so in this lesson we're going to start looking at work done by a variable force. And if the force is constant, we can fairly quickly calculate what the work done by that force is just by taking the force and multiplying by the distance that that force acts on that object. So we could take force times distance traveled is equal to work. If we graph this, we can actually interpret the work done graphically as well. So here's a constant force. I travel from position x1 to x2, a distance of d, so the work done by that force is F times d, the area underneath this curve. That's actually a pretty valuable idea because we could start to begin to figure out what to do if that force varies. So what if the force has several successive constant values? So in this case, I have force over here is one value, then it increases for a position, then decreases a little bit more. What if I wanted to figure out the work done as I pushed this object from here all the way out to here? Well, the way to do that would be to find the area in this box, which would be the work done by this force over this distance, the area in this box, the work done by this force in this distance, the area of this box, the work done by this force in that distance, and the area of that box, the work done by this force over that distance. So this can be helpful when we look at certain situations, and the one that I've picked here is to figure out the work done by a spring as it's stretched. And we'll look at springs in a little bit more detail later on this year. So the force needed to stretch a spring an amount x from its equilibrium position, which is x equals 0, is given by the equation called Hooke's law, which is F is equal to k times x. Basically, as the spring stretches more, it requires more and more force to continue to stretch the spring. Well, if we graph F is equal to k times x and find the area underneath this curve, kx times x times a half, because it's a triangle, 1/2 base times height, we get that the work done to stretch a spring is 1/2 kx squared. That is actually also the potential energy stored within a spring, and we'll talk about that in a little bit more detail. We could also use a way for if we wanted to find a constantly varying force, say in these two cases, we could do this by a succession of constant values. So say up here we're going to need a midpoint, and a midpoint, and then multiply out those areas. One thing to point out is that the area underneath, or the estimation of that force, or that approximation, gets better the more areas you use. Now for those of you who've taken some calculus, you realize what we're really doing here is an integral, find the area under the curve. But let's look at a simple example, and let's look at the work done by this force here, and I have a force which looks like it goes from 0 to 10 newtons over the first 10 meters, and then goes at 10 newtons over the next 10 meters. So what I want to do is find the area under the curve, so I'm going to break this up into a triangle. So for the first area, half times 10 times 10 are 50 joules. It looks like the second area is a square, 10 meters by 10 newtons, 100 joules. So the total area done from 0 meters to 20 meters is 50 plus 100, 150 joules. So the way to do this trick is to figure out the area underneath this curve and then add those areas up. So that's how to deal with a variable force. The thing to remember is that work done, you could calculate work by taking a force versus position graph and finding the area underneath that graph.